All right, this is Matt. I think we're on the fourth installment here, and I watched what I made previously, and I thought, well, shit, I think I might have been able to explain some things a little better, so I'll take another stab at it. I don't think I'm going to review absolutely everything, but I'll try to, again, use the cookies and pies example and maybe do one or two of these and make sure that it's clear how this works. So I've got a blank screen here. I'm going to draw somebody. I'm not an artist. Here is a person, a non-gendered person with eyes, nose, and a mouth, and maybe some hair, which is probably more than I have. And they are carrying some bags. So here is a bag of something, and here is, I don't know why, I don't know if that's a finger or what, I don't know. They should have some shoes on probably. Okay, so they're coming home. They have, this person here has come home to bring home some goodies, some treats. And before they left, or even after they arrived, doesn't matter, they said a statement. And so your objective is to figure out if that statement is true or false. And again, similar to what we talked about last time, I want to do a little bit of review here and make sure that this makes sense. So if this person comes back and says something like, I bought, how am I writing so much better today? Cookies and pies. Again, going full diabetes here. So if we think about it, we need to evaluate that statement, right? And that statement is either true or false, right? So you can think of that, and I used the words kind of input and output last time, and maybe that was a little premature, but if you think about it, that's what you're trying to evaluate. You want to figure out, is that question true or false? So the statement here is the output, right? That's what we're trying to figure out. And the way that you figure that out is by looking at the specifically the bags that have come back with this person, right? And so if we're going to figure out if they did bring cookies and pies back, we got to go look in the bags and see if there are cookies and, you know, the status of the cookies and the status of the pies. Are there any or not? So that's why we look at it, and again, I use C and P because we're looking at cookies and pies. We're looking at in the bag, are there any cookies? And then we also look in the bags, are there any pies? And so you'll recall last time we used this definition that 0 is the same as false and 1 is the same as true. And it's a convention. You know, again, I could put all these diagrams here using T and F, but because we were talking about binary, we were talking about the fact that computers operate, you know, on binary numbers, and there's a good reason for that. Then I thought, well, let's just continue on with it and just know that 0 is false and 1 is true. So we've got 4 possible, because we have 2 inputs here. We've got a C for cookies and a P for pies. How many combinations of things can you have? Well, there's only 4, right? You can have none of either of them. You could have one of each, or you could have both. And so there you go. And so we already determined, we talked last time, that the AND operator here, and I'm using the word operator, I know that kind of harkens over to math, and it's actually, you're going to find that used in a lot of places in computers, but AND here has specific meaning, not only when we think about it, right? When we're, you know, somebody says, I'm going to do this and this and this, your brain already knows what to do with that. It has to be all of these things. In math, and especially in Boolean math or Boolean algebra, that certainly has a specific connotation as well. And as we talked about last time, the only way this statement can be true is if those bags contain cookies and pies, right? If they have neither of them, well, shame on her or him. Didn't bring any back for us, and we're very sad. If they brought back just one, well, that's nice, but they said they were going to do both. They said both cookies and pies. You could almost look at the and say it's like both, right? But actually, you could have more, right? What if they said cookies and pies and cakes, or see, there's another C there. Cookies and pies and sugar, because it all has sugar in it. So let's just put sugar out there. So cookies and pies and sugar. And so you'd have three of them, right? The way it would work is only if all the inputs, okay, whatever over here, if they had cookies and pies, and if you had another column for sugar, only if they're all true does that statement become true. Okay. So let's go back and I'm going to erase here, and we're going to do another one just to reinforce it. All right, and make sure we've got it. Sorry if I'm making you all hungry. So let's do one more. And this person says, I'm going to buy, or I bought, either one, it doesn't matter. I'm going to buy. Now, actually, you know what? I should do bought, because we're talking about what has just happened. Let's be a little more clear here. I bought either cookies or pies. Okay. Again, what are we trying to evaluate? Is the statement true or false? Well, we have to go look in the bags here at some point to figure it out. So our output, again, is the statement itself. All right? That's what we're trying to evaluate, is this thing up here. And our inputs, again, well, we have to look in the bags and see if there are, in fact, cookies and if there are, in fact, pies. So, again, the combinations, well, you could buy none of them. You could buy one of them on either side, or you could buy both. And again, as we talked about last time, if you didn't buy either, well, then shame on her. None of them were bought. If I bought one of them, if I bought cookies or I bought pies, actually, let me set the first one here. If I do pies, if the person bought pies, that satisfies. That statement is now true. Right? They did what they said they were going to do. If instead she comes back and says, oh, you know what, I bought cookies, well, the statement is true. Cannot be disappointed in that. Now, the last one here again, she said, I'm going to buy either cookies or pies. So technically, while they're, hell, we might like to have both cookies and pies, but she said either. So therefore, that statement is actually false, right? This one is called exclusive OR. Remember, we talked about that. And it's usually XOR. But you can always think of, you kind of label it that way, but you could always think of it as the XOR, or the either or. Because what either means is it's one or the other, but it's not both. Okay. So I'm going to scroll down here. We're not going to talk about sweets anymore too much. And so we talked about this idea of inputs and outputs for these operators, right? So we have, what are the ones that we had? Well, we had the not operator, right? We had the and, we had the or, and we had the XOR, which was the one we just talked about. So from the last video, we had not, right? And not is when whatever the input is, if you put in a 1, the output's going to be a 0. And if you put in a 0, the output's going to be a 1. And so you could think of these, as a way to draw them. And I'm going to just draw a box here and say, whoop, I got too many inputs on that one. Back up. There we are. So this one, and the inputs are going to be on the left, and the outputs are going to be on the right. Oh, shit. This is what happens. I just push all the way up to the top here. Okay. And the outputs are going to be on the right. So we're just going to call this one not. Right? So if I put in a 0 here, I would expect to get a 1 here. And then if I go back and I put in a 1 here, I would expect to get a 0 here. Okay. And let's draw one for AND. Now remember, AND has at least 2 inputs. 1, 2, and the output over here is 1. So this one's going to be AND. And we'll just draw these out too for the same reason. We've got OR. OR has 2 inputs at least, 1 output. XOR, the same way, has at least 2 inputs and 1 output. So remember, for AND, if I put in a 1 and a 1, a true and a true on the front, on the inputs, the output will be 1. If I put in anything else on the inputs, the output will be 0. All right, so if I go and change this one to a 0, that output is 0. Or, remember this, so the only way to get a 0, if you can think of it this way, the only way to get a 0 is if all the inputs are 0, right? And if I go back here and make any of these 1, or make them both 1, right, then this output now is 1. That's me scribbling it out, right? If I put 2 1s on the front, let me go back here. If I put 2 1s here, all right, that output is still 1. All right. And then finally, we've got the XOR, the one we just talked about, where if I put in, say, a 1 and a 0, I'll get that look like a 7, doesn't it? God, let me work on this. 1. So if I put a 1 or a 0, it doesn't matter on which input. I could flip them around and do the opposite. The output will be 1. Anything else, if I put in a 1 and a 1, that'll be 0. And then likewise, if I put in a 0 and a 0, the output will be a 0. Okay? And so, as I talked about before, this is the basis for how computers are built. And it's kind of hard to believe that you could start with these little Lego blocks and come up with something that is pretty powerful, that you're probably using to listen to this whole podcast to begin with, or this little episode. So there are, I drew these as boxes, right? And of course, the inputs are on the left, the outputs are on the right. It doesn't have to be that way. The problem is if you're drawing diagrams, how do you know which one's the input, which one's the output? So there's standard symbols for this. And so we'll go and I'll show you what those look like. The standard symbol for a not or an inverse is going to be that. It's a triangle with a little circle on the tip. Whenever you see the circle, by the way, like that, connected onto a gate, and these are called gates. Okay. Think of it as an inverter. All right, it's doing a not operation. So this whole thing, the reason why it's inverting is because of that circle. So an AND is drawn this way. It's like a half circle. You have to forgive my drawing, so it looks like that. And you've got the inputs on the left side, the outputs on the right. Well, the output, there's only one output. In this case, an OR. So the OR has a little bit of a different one. It's curved, and then they come up to the top. And so, again, forgive my terrible drawing. This is an OR. And then there's an XOR, and it's kind of the same, except you've got 2 lines. And I'm not even drawing that right. Let me try. Drawing it up. So it looks just like an OR, except there's this kind of double line behind it. And the nice thing is you can then start drawing diagrams, right? And you're always going to know where the input is and the output is, because it's kind of obvious. So you could draw an AND gate this direction, right? And you know where the input is. The inputs are all over here, and the output is over here because of the direction of the diagram. Okay. So let me erase that little thing here. All right. And so what this allows you to do is to start drawing diagrams, and you can draw diagrams with these things. connected up to each other and do some pretty cool things, as it turns out. The other thing I'll mention, by the way, is that there are variations of these. So, for example, what I've just drawn here is it's called a 2-input. Whoops, let me go back to the drawing. This is a 2-input and, right? This is a 2-input OR, of course, a 2-input XOR, exclusive OR. Of course, on an inverter, inverters are always one input, so you don't have to say it that way. But you could also draw a 3-input, right? So let's go to the AND here, and I'm going to draw a 3-input AND gate, all right? And that would be this is a 3-input, right? And you could have any number. You could have a 4-input AND gate as well. And remember, the rule is, as long as all of them are 1 on the input, the output's 1, no matter what, right? The OR is, again, very similar. You could have a 3-input OR gate. If any one of the inputs are 1, the output is 1. Okay. So there's different. The nice thing is that this diagram kind of scales quite well. We can draw these in different input configurations. So let me erase that for the moment. The other thing that you're going to notice is that sometimes it's useful to think of, and you're going to see this if you go forward in this, there are times where you're going to see that you want to take the output of an AND or an OR or an XOR, and you want to invert it, which means you kind of do a NOT right afterwards. So imagine we had something like an AND. Oh, here we are. We have a 2-input AND gate, and then right after that, we want to do an inversion. So first of all, let's look at that in terms of a truth diagram. All right, so let's put the inputs A and B. I'm going to put this output of the AND here to be C, and this one here to be D. So we've got a truth table with 2 inputs, A and B. We've got this kind of interim output here, C, and then the final output, D. And let's just draw it. The combinations of the inputs, 0, 0, 0, 1, 1, 0, 1, 1. So we know how an AND works, right? If both of the inputs are 1, the output is 1. So we know that C, this is the only case when C is going to be 1. And then the rest of them are 0, right? Because it's an AND. A and B have to be 1 for C to be 1. So we've got this solved out. If you just kind of forget that whole part on D, this looks just like what we talked about before, right? This is just the AND, right? I've got cookies and I've got pies. Great, the output is 1. If I only have one of them, well, the output is 0. But now we run it through an inverter. So now we take the input of C and we go to D and say, well, what is D given what C is in the left column here? Well, if C is 0, then this has to be 1. And if C is 0 here, it has to be 1. If C is 0 here, it has to be 1. If C is 1, the output has to be 0. So we've flipped C, right? C, when it goes to, and becomes, now when you have D, D is just the inverse. It's just taking, if it's 0, make it a 1. If it's 1, make it a 0, right? This is a very common operation, so much so that they've defined other types of gates that are, essentially variants of the ones I just showed you. So let me go back here and erase this, and I'll show you what the variations look like. So, and again, I hope I haven't lost you here. So we have AND over here. Let's go over and define another one called NAND. NAND is basically just saying we take the AND operation and there's an inversion on it. And so remember I told you that circle has meaning? Well, there's a NAND, right? It's kind of taking that circle from the inverter, which is really kind of expressing an inversion, and bringing it over to the AND gate. So there's an AND. We've got NOR. Here we go. Draw an OR gate like that. Put a circle on the front. There's NOR. It's the same as having an OR gate with an inverter after it. And also, we've got XNOR. I know that's funny. Here, so you've got there. Again, circle on the end. Okay, and there's actually things that you can do with these, transforms that you can do when you can kind of move the circle around a bit. And I won't get into all that complexity here because it really just doesn't matter at this point. I'm just trying to get you, some understanding of how this stuff works and how this lady or gentleman who are carrying bags of cookies or pies can help us move into the land of gates that are in chips. And so that's basically it. I think I'm going to stop this video a little short, and we'll talk about some other things later on. I'll show you some cool things that happen with addition and how these gates can actually help us do addition in computers. And that's really it. So I hope this was fun, and you have a good day. Bye.